So welcome to this CHEM talk. It's a pleasure to introduce Gemma, who's going to tell us about, oh sorry for that noise, to tell us about electrons, ballistic, quantum interference in molecules. So the floor is yours, Gemma.
Thank you. Thank you, Camilla. Thank you, Jens Christian, for organizing. It's my absolute pleasure to be here on this lovely sunny day to tell you about some of our research. So I guess those who have heard some of my talks before will have probably heard about some of the quantum interference effects that we're very interested in. So I thought to give a little bit more of a perspective on, where it's come from, where we're, highlight, and where we're also what we hope to do with it in the next 5 years or so. But before I get to that, I thought, following in the spirit of the earlier CHEM talks, I'll tell you a little bit about me and my trajectory, how I ended up here, because as you can hear, I'm not a native Dane. No, I come from Western Australia, from Perth, which is a lovely city that we can't travel to at the moment. But otherwise, I say to everybody, I recommend, if you're ever deeply sick of Danish winter, a winter ferry, instead of a ski trip, consider Australia. Tickets are cheap and it's lovely summer down there in February. I studied at the University of Western Australia. And at that point in time, it was possible to study chemical physics, which is probably the closest thing to a nanoscience degree here, but without any of the biology. More maths, a bit more physics, and no biology. And that has turned out to really be a perfect thing for me, for my research. And I guess also why a lot of the nanoscience students fit quite well into my research group. For my PhD, I moved to Sydney, to the University of Sydney, which is also another lovely Australian city to live in. And I worked with Jeff Reimers and Noel Hush, who worked a lot with electron transfer, but my research already at that time was in electron transport. From the University of Sydney, I ventured out in my postdoc. Well, actually, before I went anywhere else, I had, I guess, equivalent to a change of environment. And within sort of the first 6 months of my PhD, I got sent to Copenhagen. In fact, the very first week I started my PhD, my supervisor said to me, "Oh, I met these guys at a conference. They've got this code you should use. You should go to Copenhagen." And I said, "When?" And he said, "As soon as possible." And I said, "I'm not ready for that." so we waited 6 months, but then I came here and I worked with Kurt Stockberg, who at that point was at DTU. And then pretty much the week I arrived, moved to KU. And I guess many people will know him. He went on to found the company that is now part of Synopsys, the software company that produces Quantum ATK. And so I met Kurt. I sat with Thomas Bjornholm's students, who also many of you know, over in the D building at that time. And I also met Kurt Mikkelsen, and as part of that, got introduced to a young PhD student who was in Kurt's group at that time. And Torsten and I have had these careers that have, tracked each other, because after we finished our PhD, we both then went on to Chicago, and we went to work with Mark Ratner at Northwestern University. And this was a fantastic time. It was a really wonderful, exciting big group of people doing exciting things. And I guess both of us still have a lot to do, both socially and in terms of our collaborations with all of the people we worked with from that point in time. So I know this thing of moving around as a PhD student, as a postdoc, a lot of people talk about it as one of the challenges of an academic career. But I think I mean, from my point of view, it has certainly enriched my life and my career. And then in 2010, I moved to Copenhagen. So I've had, over these years, I've had a big group, and then I went back down to a really small group, and the group's now growing again. And I was saying to my group this morning, there are strengths and weaknesses to big groups and small groups, and I've been enjoying it along the way. But through this time, we've been sort of developing our research in lots of different areas, but one of the themes that has carried all the way through from my postdoc has been this interference work. So when I'm not doing all my normal work, I also have another sort of a job on the side, and that is that I work as a senior editor for the Journal of Physical Chemistry A, B, and C, and just this year started as the deputy editor, actually in charge of ACS Physical Chemistry Gold, which is the new open access physical chemistry journal from the ACS. So I guess most people know me for that, but I'm also always happy to be a second opinion if you have a cryptic message from an editor or referees, or want some feedback on a cover letter you're planning to submit to a journal. My door's always open to give any sort of feedback on that sort of thing, for whatever it's worth. That's not to say that we have a perfect track record and all my manuscripts go straight through. So the research that I'd like to talk to you about today is, I think, really exciting sort of melting pot of chemistry and physics. And I would say, it's when quantum interference meets molecules. And of course, because we're talking about quantum effects, the sort of starting points you could think of is, it is, the beauty of coming down to the atomic scale means that suddenly quantum effects start to dominate. So this, of course, is a cartoon of the Bohr model that we are all presented with as often, and at least in Australia, it was, the very first picture of atomic structure that we're given. And when I came to Copenhagen the very first time, and I discovered that, the Bohr Institute is there with Niels Bohr's office still sort of in place, and this was a very exciting discovery. And I was also given a small book of Niels Bohr's original papers. And I read these papers and I thought this was a revelation, in that, I feel like we're taught the Bohr model as, here's the Bohr model and it's wrong, is almost the thing that you're told in the second sentence. But as an interesting exercise for that sort of thinking about the process of scientific discovery, reading these original papers, you can see the thinking that went into the visionary leap that it was to develop this model. And of course, what was important about it from a theoretical point of view was also not just that we had this sort of picture of atomic structure, but you could solve problems with it. Like all of these things, that's what makes theoretical models useful, is when we can start to say something sensible about the world on the basis of that theory. So, this idea that we are introduced to the Bohr model, we have this picture, but it's wrong. Then you come to, okay, so what is there instead? And of course, the next thing we're introduced to is atomic orbitals. So instead of this sort of planetary orbits that are the feature of the Bohr model, we have these orbitals. And orbitals, of course, don't have just this sort of spherical symmetry always. We see the sort of different p orbitals, but also, you lose the sense of the position of the electron, the path that the electron's taking, because of course, what we need to describe is the wave function, right? We're describing, the wave function, and that's, this sense of thinking about something, it's a particle, it's a wave, what is this? And on the one hand, sometimes when we talk quantum mechanics, it's like we're sort of told to throw away our intuition, because this is this new world where both particle and wave character can dominate. But actually, some of the intuition we have for wave properties is not so useless. We have a strong sense from the sort of macroscopic world of wave behavior. We know, a raindrop dropping on a surface and you'll see a wave packet emanating out on the surface of the water. Similarly, many waves interacting, we're going to see interference patterns. When peaks are meeting peaks, things can get even higher, but a peak can meet a trough, and we can have this sort of destructive interference effect that waves are cancelled out. So this is our picture of wave behavior in the macro world. I think I went to university determined to study law. And in fact, I started a law degree, but in Australia, you could not study straight law as an undergraduate at that point in time. You had to do something else. So I chose to do science alongside because I thought that was straightforward. And chose physics, chemistry, and maths as my science subjects. And at the end of my first year in physics, they put on the Feynman lectures, videos of the Feynman lectures in a big auditorium at lunchtime. And when I saw this lecture in particular, this probability and uncertainty, this was sort of, I guess, probably the first thing that made me think that the science wasn't just something I was getting through so that I could continue with my law degree. This was something that really captured me. So if you haven't seen this, Bill Gates brought the rights to these and made them publicly available. They're amazing. Everybody says you can learn a lot. You walk away, he's an incredible educator, you walk away with this sense that you deeply understand what's going on. At the same time, if somebody were to give you a problem set to solve on the material, you find out that you can't necessarily solve very much after listening to these lectures. But they're great scientific entertainment and education in that sense. So this particular lecture is what's known as sort of relates to the Two-Slit Experiment. And this is a thought experiment looking at electrons. But the thought experiment starts with this sort of two-slit kind of setup and saying, what if it was bullets being fired through these slits? What if it was water waves sort of passing through the system? And what if it was electrons? So this cartoon here is what you'd see if it was electrons. So they have this particle sort of nature in that they're fired, coming as discrete particles from this gun that's a sort of G in there. And then when they're measured at some detector, and this is, you can see that with the X out there, you can see this sort of pattern of the, where the probability of where it's increasingly likely to find the electrons. And of course, this is not the pattern you would expect to see if it was just particle behavior. That's not what you see with bullets, but it is what we see if it is water waves. And this sort of pattern is coming from interference effects, and for the water waves, it's like two wave packets emanating out from the two slits. But in our case here, it's now the electrons, and it's an interference effect with the electrons that sort of has a probability of passing through both slits. So this is kind of the picture that you have from this lecture. So we're interested in looking at current through molecules. So electrons are one of the fundamental carriers of charge. They're what allow the current to flow through molecules. And you could ask the question, this interference pattern is allowing the electrons, they move through some places. You have these bright spots and dark spots. So can we use this interference effect to turn the current on and off in molecules? So in my group, we studied this computationally. We have sort of molecules in idealized junctions, typically. But within this setup, we can study lots of different things. We can look at sort of chemical variation in the molecule, geometric sort of variation of how the molecule sits, different substituents, different conformations, vibrational motion, molecule-molecule interactions if we had a monolayer instead of single molecules. And with all of that, what we actually calculate is something called the transmission. So it's a probability, in some sense, for an electron to pass through the molecule as a function of energy. It's not quite so simple as being a probability. Sometimes it goes above 1 because it's actually a probability per channel, and there's sometimes more than one channel in a molecule. But this, I'm showing you down the bottom on the right-hand side there, is the transmission as a function of energy through a benzene diethyl molecule that we have in a gold junction. And just sort of illustrating, you can see where all the molecular orbitals would be. If we plotted as a function of energy the occupied orbitals from that molecule, you can sort of see them lining up under this broad peak that we're seeing in the transmission. And it turns out the molecular orbitals have something to do with, what energies it's very likely for an electron to pass through the molecule, and which energies it's very difficult for an electron to pass through the molecule. The sort of the details of, that relationship between orbitals and electron transport are complicated. But what you can see, and I guess what you hope to see, is if we're thinking of this idea as a molecule being sort of many slits in some sense, the analogy with the two-slit experiment, we have these many orbitals. We do have this sort of complex quantum object in a molecule. And to that extent, it seems possible that we might be able to have something like a two-slit experiment from a single molecule. So that's what we're hoping for. Can we turn the current on and turn the current off with something like interference effects because of the sort of multiple paths, in some sense, that we have for an electron to pass through a molecule? So, of course, I wouldn't be talking about this if we'd never had any success in this direction. And again, the result I'm showing you here is one of our highlights. So on the left-hand side, we have a silane, a linear silane. You can see this sort of the black dots here. It's like permethylated. So as opposed to an alkane where you'd expect to see sort of CH2 groups there, we've got methyl groups on each silicon atom. And then everything you have at the ends, CH2 SME, this is the binding groups. So these are the units you can see that actually kept the same on both molecules. This is the part of the molecule that allows these systems to bind in the gold junction, both in theory and experiment. So we compare the one we call silicon Si4, which is sort of the linear 4-atom silane, with the one that I'm calling Si222. So this is a bicyclic silane. What you can see, you have these two silicon bridgehead atoms that we've labeled Si, and then you have these three sort of 2-atom bridging paths. So you can, if you look at that sort of in an analogy, you can imagine in an atomic structure sense, we've actually got 3 4-atom silicon paths through that system. This is what the bicyclic system looks like in a space-filling sense when we put it in a gold junction. So if we compare the transmission through these two systems, this is what we see. So energy here, if you think, okay, what does energy mean? This is the energy, so our x-axis, the energy scale, has got something to do with the incident, sort of like the incident energy of the electron that's coming from one gold electrode coming to the molecule. You could also think of this in terms of momentum. But you can see that across a very broad energy range, the purple curve, the Si222, is much less transmissive than the Si4, the all trans case. So this, the important energy, if we want to compare with an experiment, is, I can see that somebody is not muted, and I'm not going to be able to find you, but if you could just check and mute yourself, that would be wonderful. So the important energy to compare with the experiment is 0 on the scale. This is the energy at which the sort of electrode Fermi energy is. And so at low bias, if we do this sort of measurement at low bias, that's what we see. So you can see this system's much lower. Then, you know, how much lower makes something exciting? And so this sharp dip we have is the signature of quantum interference. That's great. But, you know, what about it makes this significant? So when we first started thinking about interference work, we started that actually during my postdoc. And we were playing around and we were saying, okay, when is this significant? What makes this really exciting? So we typically think of the transport through these molecules as tunneling transport. And we said, okay, well, it would be really exciting if we could come up with a molecule that was more insulating than vacuum, right? If you sort of think of comparing a molecule with vacuum as a tunneling barrier, typically we say, well, a vacuum, you know, there's no electrons there's no nuclei there. So surely it's harder for an electron to tunnel through vacuum than it is through a molecule. And that's the case in most instances. So that was our sort of 10-year-old goal for when interference effects get really exciting. So in the calculation, we can sort of do that. Because what we can do is we can say, well, I can take this 2-2-2 structure and I can break all those bonds across those bridges. I need to passivate those two bridgehead silicon atoms, but so I can make something like this. So I can just leave the bridgehead silicon atoms there, and then I have a gap. And then the question is, if I have that gap, what does that mean in terms of the transmission through this molecule? So this is what I see. So now you see the cut system is much higher across a significant energy range. We're on a log scale for our y-axis on the transmission here than the 2-2-2 structure. So I broke those bonds, put a gap in there, and the probability of an electron passing through went up. Okay, and so this was into the realm of when we think this is exciting. So it actually turns out if you wanted to say, okay, how big does this gap need to be before I reach the level of the 2-2-2 system? You actually have to stretch approximately 1.5 extra angstroms. So that's like a carbon-carbon bond longer until you reach the level of the system with interference. So that was you know, very exciting. And as you can see, we were lucky enough to have this published in a very nice journal. But then you could sort of cycle around again and say, okay, but you set this up saying that this was something like a two-slit experiment. You know, this is our sort of classic case for interference. And with these, you know, 3 parts, it's tempting to say, oh, it's different arms. You know, this is our different slits through the system. So this is what happens if we sort of map the pathway of the current through this molecule. And you can see it's not so simple. It doesn't look like, you know, 2 nice slits and 2 nice paths through the arms. Actually, our interpretation of this is so it's actually, you can see it's only 1 arm that really dominates. The other two arms are really just holding the structure in place. They're sort of rigidifying that central unit. And actually, our interpretation of it is it's sort of interference most likely between a through bond and through space path. You can see there's an arrow there from bridgehead to bridgehead silicon atom. So that's where we were with an exciting sort of system. But you can also ask, okay, so with the two-slit experiment, I say, oh, it's waves emanating from one path and waves emanating, you know, from the other slit. That's our 2-part. That's the what's interfering with what, right? And so if I just told you that, you know, it's not so clear here, you know, what is the general picture of the sort of what's interfering with what in molecular systems? So I would say now we can sort of go somewhere to answering this question by considering benzene. When I was making slides for this talk, I realized I had actually never included the results from this paper in a talk I had given before. And that was because this paper came at a time where we published a whole bunch of this interference work. And, you know, at that point in time, I was a postdoc, and when you're a postdoc, you give whatever, 10-minute talks if you're lucky at a conference. So you're more likely to choose the results from your JAX paper than from your CHEM Phys paper. But this, I think, is an interesting story in that it takes all kinds of papers to develop understanding. So this is CHEM Phys, which, if anybody knows, is a journal with a, depending on whether you look, 2-year, 5-year impact factor of just under 3. So we're not talking about some exciting journal. This is also a paper that we did entirely with a Huckel model in Mathematica, rather than any particularly sophisticated calculation. I think a bachelor student could do it, and my bachelor students now do write these sorts of code. But this paper actually has over 200 citations now. So it takes all kinds of papers, and you never necessarily know which one is going to grab everybody's attention. So consider benzene, because this is one of the classic systems for interference effects. And where we see interference effects in benzene is if we look at different substitution patterns. So we're imagining, if you look at the little cartoon I've got down there, one electrode we always have at the black side. And then we can say, okay, we can take a sort of para substituted with the green, meta substituted with the red, or also substituted with the blue. And you can see when you look at the transmission at 0, the meta substituted case has this great screaming dip in the transmission, whereas the ortho and para substituted have the same sort of high level of transmission. And there's probably some people in the audience that are also thinking at this point that, hang on a second, this all smells like a bit of a con. You've set this up as it's all very interesting, it's quantum interference, and now you're telling me there's a difference between meta and para substituted benzene. So this is the funny game, because that result is not shocking to a chemist. That is, completely unsurprising. And this is because, this interference effect, as we call it, is also, influencing all kinds of other properties related to electronic communication across the benzene ring. So all kinds of things we know about chemical reactivity and substituent effects are also subject to this same sort of modulation of electronic communication. But if we take this system, there were people that wanted to say, oh, this is like, electron going one way around the benzene ring versus electron going the other way around the benzene ring. It's our two paths. But, also I think from a chemist's point of view, we tend to think of benzene much more as, a single object rather than, two isolated paths. So this idea, when we looked at this, the picture we came to was, you can see you've got all these sort of peaks in the transmission. These are coming from the orbitals. And I told you there's sort of contributions from all of these orbitals. So when I sit in the middle of the gap, I can sort of think, well, I've got these tails of these contributions from the orbitals. And it seems like in some cases, namely the ortho and para substituted cases, I have constructive sort of interference between these tails. Whereas in the meta case, now it's the same tails coming down, but now we're getting destructive interference, and something's changed with the symmetry. So we can say that in words. Quantifying it in numbers is sort of surprisingly more difficult. And that is because actually, the bits we have in the transmission are complex numbers that are first summed and then squared, right? So it's not that we can do sort of some nice peaks from the orbitals, but if we plot these sort of complex number contributions from the different orbitals, we get something like this. So in the top line, I'm summing the real components, and in the bottom line, I'm summing the imaginary components. The thick black lines are the sum in each case, and the coloured parts are the contribution from each orbital. So the ortho case on the left and para case on the right, you can see that in particular, so the imaginary parts cancel, but the real parts that you see on the top line, the solid black curve isn't crossing 0. And that's because these tails of these orbital contributions are constructive. Some are bigger than others, some are positive, some are negative, but the net effect is, a constructive non-zero contribution. In the middle of the metal case, you can see it's the opposite. Both the real and imaginary components are sort of balanced in this way that every orbital contribution has an equal and opposite signed cancelling contribution. So for example, in the top plot, in the real part, the green is cancelling with the red, the yellow is cancelling with the blue, for example. Okay. So this is our sort of working picture of what's happening with interference effects. And there's actually, turns out, a lot of things people can do with orbital pictures and interference effects. And this sort of brings you back, we do all kinds of sophisticated calculations in my group, but we also do plenty of Huckel theory. And we use that, we really enjoy using that with bachelor project students in teaching, because there's actually lots of things you can do for this type of molecular electronics, just looking at Huckel theory. Okay, so for the final maybe 2 minutes, 3 minutes, I'm going to tell you a little bit about where we're going now, because I guess I thought that is probably an interesting perspective, and maybe it's interesting for other people thinking about, okay, how do you go further with something? You've got it all worked out, so what? So the project we have now, the big project in my group, is saying, okay, well, where can we push these interference effects? So one of the other sort of experimental things people have seen is something that looks like these interference effects in non-bonded systems, so pi-stacked systems. And so you can say, okay, if we can see interference effects across two molecules, can we design whole sort of materials? Can we design monolayers? Can we design interference effects that, have a sort of a many molecule effect? What does that even look like? What sort of structures do we need? What sort of, at room temperature, what sort of length are we actually seeing phase coherence over in molecules? Given that we have evidence of phase coherence across these molecules, we wouldn't see these interference effects if we didn't have phase coherence. And not only, this is at room temperature in solution when it's sort of a chemist's intuition. Then you can say, well, can we do something with that phase? I mean, there's all kinds of excitement and interest in quantum computing, in this sort of quantum systems. But if we have this phase coherence, what in a molecule controls the phase of the transmitted wave function? So we can start to look at that and just ask fundamental questions about how chemical structure controls phase in these kinds of processes. The other thing that we are interested in is not just electron transport. So we know that there's results that show that substituent effects can have a massive impact on vibrational energy redistribution. And so what about, can we extend this sort of framework of interference effects to heat transport or vibrational energy redistribution? Can we use that, to make a thermal insulator, or to change a reaction product ratio? If you have a chemical reaction where there's some sort of dynamical effect, some sort of vibrational excitation that is, changing the part of the potential energy surface that reaction is sampling. So they're the sorts of ideas where we're trying to step out with these interference effects. I would say, watch this space. Maybe next time it's my turn for a chem talk. There's some interesting developments there. Finally, I've included all the people that were involved in the research projects that I talked about today, the people that have been so generous to fund all of this work, a couple of pictures of my group. Thank you very much for your attention.